So in the last screencast, we developed an expression for the angular momentum of a multi-particle system about an arbitrary point Q. Remember, there's no restrictions on this point. It can be fixed, it can be moving, it can be anything that we'd like. This is a useful relationship in and of itself because we can convert between these two angular momenta. But as always, these expressions become most useful when we apply Newton's second law in it. So what we want to do is start by taking the time derivative of this expression. And so here we've taken the time derivative of each of the terms, where we have the time derivative of the angular momentum about the center of mass, and then distributing the time derivative into the cross product, the time derivative of the first term crossed with the second term, and then the time derivative of the, and then the first term crossed with the time derivative of the second term. So let's see what we can reduce in this expression. Take a look at the first term, and we have the time derivative of the angular momentum about the center of mass. We've dealt with this before. When we had the separation of total angular momentum, then we had the time derivative about the center of mass and the time derivative of the center of mass about an inertially fixed point. And so this expression, we call this the moment about the center of mass due to external forces that are on the multi-particle system. In the next term, we have the time derivative of the position vector of q with respect to g, and that's equal to the velocity of q with respect to g. This is convenient because we now have the velocity of q with respect to g crossed with the velocity of q with respect to g. So any vector crossed with itself is equal to 0, so our second term goes to 0. And then our last term helps us get to Newton's second law because we're taking the time derivative of a velocity, and Newton's second law is based on the second order term, the acceleration. So if we take the time derivative of the velocity of q with respect to g, then we get an expression in which we have the mass of all the particles is multiplied by the acceleration of q with respect to g as observed in an inertial reference frame. But to apply Newton's second law, or to get this, we can't have an acceleration that's a relative acceleration at q with respect to g. So let's work on this in terms of a form that's related to an inertially fixed point. So we'll rewrite the acceleration of q with respect to g as observed in an inertial reference frame as acceleration of q with respect to O minus the acceleration of g with respect to O. Now we can do a little bit more work on this expression to make it more palatable. And to do that, we're going to relate a couple of our terms to the forces that are external on the system. So our moment about the center of mass is related to the external forces because it's caused by external forces. And then the acceleration of the center of mass is also related to the external forces by Newton's second law. And so we substitute each of these expressions into our time derivative of the angular momentum, total angular momentum, about an arbitrary point Q. And so then by collecting our cross product terms that include the summation of the external forces, we're left with a nicer looking expression in which we have a moment term here, and then we have what should resemble the inertial moment that we've seen before. And so our moment specifically is r cross f, and the r is a position vector to each of the particles, but instead of being related to the center of mass, like we had with this external moment, we now have the position vector that's related to our arbitrary point q. So this is the moment about q due only to the external forces that are on the multi-particle system. And so our final form looks like this, in which we have the time derivative of the total angular momentum about an arbitrary point q, all observed in the inertial reference frame, is equal to the external moment about point q, and then it's plus this term, which reminds us of our inertial moment. We have our position vector from g to q, or q with respect to g, crossed with the total mass of the system multiplied by the acceleration of point q. Now this is the inertial acceleration of point q. Now, separate from this, we developed, using the separation of angular momentum, that elegant expression in which we have the time derivative of the angular momentum about the center of mass is equal to the moment about the center of mass due to external forces. And although we developed this expression separately or independently of working with this generic form of the total angular momentum about point Q, if we choose point Q to be g, then we see that the time derivative of the angular momentum about point G is equal to the moment of point G due to external forces, so the moment's about the center of mass. And then here we have Q with respect to G, so G with respect to G, and so that would make this equal to 0, and so then this entire inertial moment term goes to 0, and then we're left with the relationship between the angular momentum with respect to the center of mass and the moment about the center of mass. Now, seeing this comparison between the two forms does beg the question, when would we ever need to use this generic form of the time derivative of the total angular momentum about an arbitrary point? And it does come in handy when it's not geometrically useful to find the center of mass. We see that occasionally in multiple particle systems. Typically, the center of mass is easy to find in multi-particle systems. But this is regularly applied in rigid body systems, and that's primarily where we're going to use this concept. So in summary, what we've done is we've taken our angular momentum in a multi-particle system about an arbitrary point that we've developed that expression in the last screencast, related that to the angular momentum of a multi-particle system about the center of mass. We've then incorporated Newton's second law into this, which gives us insight about the dynamics of the system, and then with this expression we'll be able to develop the equations of motion of a multi-particle system using an arbitrary and generic angular momentum form.